Greetings, everybody. This is our week six of lectures on video. And this particular week we had a short one because of the snowstorm, but we switched gears and began to discuss computation domain and introduced some of the algebraic structures that provide a basis for computing, computing in general. And so the structures we talked about were groupoids, semigroups, monoids, and groups. These four structures constituted our focus. And among these four structures, groupoid is the structure that just happens to be closed under an operation, which I denote here by an asterisk. And the example that I have is that of a finite set of elements, which are rock, scissors, and paper. And I'll illustrate this on the next slide. And then the semigroup is a groupoid with an associative operation, again, which we denote by an asterisk. And for an example of that would be a set of all binary strings. Monoid is a semigroup with identity under the same operation that we defined here, one operation that is, and then we take set of all binary strings and add to them the empty string. Then we get a monoid. Group is a monoid with inverses. So like set of integers mod n would be an example. So let's look at some specific examples. As I said, a groupoid is a structure with a single operation. It doesn't have to be associative or commutative. This particular example is one that is commutative but not associative. And so we have three elements: rock, scissors, and paper. And in this table we'll list them along these columns as well as along these rows. And as we do, we then create our table. So rock and rock gives us a rock. Rock, scissors basically give us rock, and rock, paper give us paper. And so the rest of the table is filled out the same way based on the game of rock, scissors, and paper. If you ever played this game, you would know how these pairs of choices would lead to a winning combination. So this group is not associative, as I said, because if you look at, for example, rock, scissors, and paper and perform the computation in this order, you will see that you get paper out of this because rock will actually take care of scissors here, and then rock and paper will be paper result-wise. And here you just switch the order of computation. You say rock, and then you first say scissors and paper, and then say rock with them. So scissors and paper will give you scissors, and then rock and scissors will give you rock. So the results are different, and therefore the process of computation is not associative. But it is commutative, as you can see. Rock and scissors will be rock, and scissors and rock will also be rock. Or you can have rock and paper, or paper and rock, paper, or rock and paper, paper here. And the rest of the table is also commutative, which is to say that A times B is equal to B times A. That's what we call a commutative operation. So a semigroup in monoid examples would be, as I already hinted, binary strings like these, all of the binary strings, not just some of them. And this is clearly closed under the string operation, that concatenation operation that we use. If you take any two of these elements in this set and concatenate them, you get another element in the same set, so it's closed. It is associative because if a string operation is associative, you can actually proceed in order in terms of like concatenation. and you'll get the same concatenated string. And so monoid would be the same string set here, except we also add to it the empty string. And that gives us the identity, because then you take empty string with any one of these strings and you get that string. And that's kind of like the identity. Something, the operation plus identity is always that something. So a group is the, I guess, the most structured element out of these four. And inverses exist. And here's your mod 5 addition, where you could see that in each of these rows we have a 0, which is our identity. And that simply attests to the fact that these elements all have identity, like 1 and 4 add up to 0, meaning that 1 and 4 are inverses of one another, and 2 and 3 are inverses of one another, and then 4 and I guess we already mentioned these things. So 2 and 3 are inverses of one another, 1 and 4 are inverses of one another, and 0, of course, is its own inverse. So every element has an inverse, and of course when these inverses exist, they are unique. This can be established. So that's what a group is. And of course, if I were to indicate this structure-wise, a group is contained in a monoid, and monoid is contained in a semigroup, and a semigroup is contained in a groupoid. So we could actually indicate it. Let's see if I can go back here. There's any space there. I could possibly write this down here somewhere. So that way we get to that. Okay. So groups contained in monoids, which are contained in semigroups, which are contained in groupoids. That's how the relationship works. Another way of saying this, of course, is every group is a monoid. Every monoid is a semigroup. Every semigroup is a groupoid, because converses are not necessarily true. So just going back, we looked at the group here, and then the next thing that we want to look at the symmetric and cyclic groups. So the symmetric group is denoted as S sub n, the set of all n factorial permutations of degree n. The degree meaning the number of symbols that we use to create these permutations. So here's S3, which is expressed in what we call the cycle notation. And all this means is that 0 goes to 1 and 1 goes to 0. And likewise, this means 0 goes to 2 and 2 goes to 0. And here, for example, 0 goes to 1 and 1 goes to 2 and then 2 goes to 0. So that's a cyclic notation, or the cycle notation rather, with which we express these permutations. Of course, identity, one that fixes everything to itself, 0 to 0, 1 to 1, and 2 to 2, is denoted by E. And in two-row notation, which is also used, we could express these permutations like so. So 0 goes to 0, 1 goes to 1, 2 goes to 2. And this, of course, is 0 goes to 1, 1 goes to 0. And that's how you write it. 0 goes to 1, 1 goes to 0. And the 2 that is not actually included in here goes to itself. That's kind of like omitted from the cycle notation we have here. And likewise, 0, 2. That means 0 goes to 2, 2 goes to 0, so 0 to 2, and then 2 to 0, but 1 is fixed. One of these longer ones, 0, 1, 2, 0 goes to 1, 1 to 2, 2 back to 0, and that's how this is. Actually, this is the third one, and this is the fourth one here, which is 0 to 1, 1 to 2, 2 to 0, which is this map. And finally, that one is 0 to 2, 1 to 0, and then 2 to 1. 0 to 2, 1 to 0, that's what this is, and then 2 to 1. Now there's also this thing called cyclic permutation group of n elements. And in this situation, C5 example, we pick ourselves 5 symbols, and then the permutations we have are identity, 0, long cycle we call it, 0, 1, 2, 3, 4, and then 0, 2, 4, 1, 3, 0, 3, 1, 4, 2, 0, 4, 3, 2, 1. And as we shall see on the next slide or two, this really constitutes a group, meaning that it's closed under the composition of permutations. That is to say, if you take any two of these and multiply them, then you get something that is in the same set. In the two-row notation, these same permutations are written as 0 to 0, 1 to 1, 2 to 2, 3 to 3, 4 to 4, etc. And then for the next map, this was the identity, 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 0. That's what this map is. This one is 0 to 2, 1 to 3, which is what this is, 2 to 4, which is what this is, 3 to 0, and then 4 to 1. And then the rest of it is written the same way. So now there's this important theorem that I mentioned in class, which basically ties finite groups together. And then I just skipped the letter Y here. This is called Cayley's theorem, which was actually proved by Cayley around 1860s, quite a while ago. But basically what it says is every finite group is isomorphic, that is to say equivalent to a subgroup of the symmetric group of an appropriate degree. The degree is something that you have to fix, but here's an example. Modulo n addition group, which is denoted as Zn, is isomorphic to Cn, which is the cyclic group of permutations on n elements. And the isomorphism is actually generated, this is why Cayley's theorem is so powerful, by way of taking the first row, which is this one here, with each of the remaining rows as you construct your permutation. So like if you look at the first row here and then the second row here, you can see the map would be the permutation that we will identify this row, which is this element 0, with 0 to 0, 1 to 1, 2 to 2, 3 to 3, 4 to 4 permutation. So this first row element in this first row, 0, becomes permutation 0, 0, 1, 1, 2, 2, 3, 3, and 4, 4. And likewise, the second element, 1, is identified with the next permutation, which is obtained by taking the first row and then the third row here. The first row and then the third row. So 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 0 becomes 1. And of course, just moving along the same way, we get to go to the next element, which is 2, which then is generated by this permutation or identified by this permutation, formed by taking this first row with this fourth row. So 0 to 2, 1 to 3, 2 to 4, 3 to 0, 4 to 1 becomes element 2. And then likewise 3 and 4. And so those permutations, there shall be exactly 5 of them. The first pair, the first and then the second, I guess the third pair here, the third row, fourth and fifth and so on, will give us this table here. So identity, and P is like this element 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 0. P squared is that element that actually is obtained by multiplying P by itself. And then of course P3 is the element that is obtained by multiplying P by itself 2 times, and then P4. And then they give us this particular table. And these two tables are identical. They're equivalent, if not identical. And so 0 is associated with E, 1 is associated with P, 2 is associated with P squared, 3 with P cubed, and 4 with P4. And if you add, for example, let's say 1 and 2, you get 3. And if you just multiply p and p squared, you get p3. Like here, p times p squared is p3. And here, 1 plus 2, which is like 1 plus 2, is equal to 3. So the structure on the left is really preserved by the structure on the right. But now we really have two different groups. One is identified by these elements of Z5, but the other one here is identified by permutations on 5 symbols, which we have written up here, 0 through 4. So Zn is isomorphic to Cn is basically what this is stating to us. And the elements 1 and p are identified together. Once that happens, all the other elements connect together. I could possibly state this somewhere by saying that, let's see if I can write this up somewhere. There's not much space here, but let's see if I can try it here. Element 1 and permutation P are the generators of the two groups, and they are mapped under the group mapped to one another. Under the group isomorphism. Okay. So this establishes, let's see if I can just do this super quickly. Okay, so this can all move up a little bit. I take this up. So this gives us what we really want, which is to say that we now have an isomorphism that ties things together, and we're going to use this next week to actually build circuits to compute addition in terms of permutation switching. So that will be next week. We're going to cover also more algebraic structures, and then, as I said, look at circuits or permutation switches that actually allow us to do these computations that are more, I guess, arithmetic in nature. So until next time, take care, and I'll see you in class on Wednesday, which is, I guess, today.